after our extended little break. So basically where we started there last week after a little, was objective 4, which is non-condensable gases in the system, how to get rid of them. The 2 ways, of course, to get rid of non-condensables, manual, okay, and then auto purging, manual and auto purging, remember, okay. In other words, air, you have to get rid of, as you know, one of the 3 nasties. This was the, this system here, if you remember, was basically the manual purging system. This is a good thing to know because the auto systems work on the same principle as this. And what you just got to remember here, but this type of system here is that you have a coil inside that you use refrigerant from the system basically to boil off any of the non-condensables and the refrigerant that's entrapped in the basically the level of the non-condensables in the liquid that's inside this unit itself. And this right up here actually goes through that bit by piece, but you got to remember it's the main thing is that there's a procedure to do it. You have to basically bleed out the non-condensables. You've got to charge it with some refrigerant to get the coil to work properly, and then you have to manually drain it so that the non-condensables are emitted to the atmosphere, and then the rest of the vapor that you use in the system to get rid of them will go back to the compressor itself. Okay. I won't ask you to draw that by any means, but you should know how it works, because if I do ask you, I'll provide you with the drawing. The next thing that we did is objective 5, which was moisture in the system. One of the other 3 nasty moisture in the system. Okay, of course, wet moisture and heat transfer, and of course, corrosion and all sorts of other level things. And then we kind of ended off from there, and then today we're going to start here, which is refrigerant addition. Okay, so I'm going to give you a proper procedure for that, which is kind of a hybrid. Then I'm going to talk about the difference between an ammonia system and a standard system itself, like the old R1 company system, 406 system. Okay. All right. Yeah. Okay, so how do we charge a system? Okay. Now, first of all, why do we charge a system? When do we have to charge? When do we have to? Well, there's only 2 scenarios why we have to add refrigerant to the system. Okay, and that's one if it's going into service when it's first being built, or after it's been first constructed, or if it's been running for a while and the system has become short. Okay, so purpose of charge or adding addition or the addition of refrigerant to a system. Okay. system, and it's being charged for the first time. Or system that's already running, a system in operation. Okay, system in operation is in need of some additional refrigerant. Okay, I'm gonna refresh. That's gonna be short form for refrigerant because I'm gonna have to write it out 9 million times today. All right. Okay. So there's the two purposes of charging a system. Okay. Now, okay. Now, I'll draw a diagram in a second. Okay. Okay. So how do we do it? All right. So there's a description of purpose operation. Let's say sort of the operational side of it. How do we carry it out? Okay. So where do we add it? It can be recharged. Okay. Recharged. Okay. Or charged. Another way of looking at it, charged initially. Okay. Okay. And it's done by adding refrigerant to the high pressure side. Okay. Okay. And if it's done, obviously, in liquid form. And I'll explain a little bit more of this in a minute. Okay, obviously. It's done in liquid form. Okay. So where do we add it? Okay, so where do we add it? Just before the expansion belt. Or, big caveat, you can add refrigerant gas, okay, to the low pressure tube, to the low pressure side, okay, caveat, low pressure side, before the compressor inlet. Okay. Now, this, okay, you won't be doing this in your job. Only the refrigeration tech can do that. But you just want to be made aware of it. 90% of the time, anytime you'll be involved in charging or charging a new system or after it's been worked on, right? Okay. But those guys will it takes a little bit of a knack to do that, but they'll be doing it on that side. Okay. But again, I want to stress that. Okay. Normally, only liquid, okay, refrigerant is added. Yeah. All right, so I'm going to take a little drawing here for you. Now there is a drawing in here, but I'm going to change this because what I'm going to do as well is I'm going to go into everything about the king valve. I'm sure you've heard about the king valve by now, but I'm going to give you the proper terminology and what the king valve is as far as refrigeration systems go. Because there is questions on your search about the king valve, and this is the only explanation that you need to know about refrigeration systems and the king valve that I'm about to tell you. All right. So I'll wait till everybody got this. Yep. Okay. All right. So I'm going to make a little drawing over here to the right. All right. So this is our evaporator here. Charge cylinder. Weight scale on that. I'll explain all this as we go along. Weight scale. That. Over here we have, okay, this is our liquid receiver. And we have a return. Okay. We return back. Here, over to here, right here. Okay, all of that is our expansion valve. Okay. Start that. Good. So, this is NH3 or ammonia. Okay, and that is liquid from, okay, I'll read that a little better, from our condenser. Liquid refrigerant. Okay, and that's from the condenser. Here. Okay. And we're going to put also on here, we're going to put one little safety valve too. Which we're going to get into today as well. Okay. So, this is our liquid receiver. Receiver in our system. Right? This is the king valve. Right there. King valve. This is what we call the charge valve. Right there. Okay. So, big misnomer or mistake is people make the mistake of calling the king valve the fill valve. It is not a fill valve. Okay? The king valve, its sole purpose in life is to isolate the receiver and the liquid refrigerant from the remainder of your refrigeration system. Okay? This charge valve is something that's a separate entity. Okay? And if you'll notice down here, this is what we have a refrigerant cylinder here. Okay? Or a charger, whatever you want it to be. A charge block or whatever, okay? This here is a scale. Okay? So I'm just going to briefly go through the procedure for it, kind of write it out for you. So normally what happens, we're going to say that our system is, we'll also get into this, but it's completely new, and it's ready to be charged for the first time. And it's been tested and certified, the kids say they signed off on it. Okay? So what happens is the refrigeration tech guy will come by and he'll have a bunch of these cylinders either on a truck in bulk or he'll have a bunch that are weighed. Okay? And normally all systems are charged by weight. Okay? By the amount of kilograms or weight of refrigerant it's in. So what happens is he'll physically come by and we'll flip this up, there's an isolation valve there. We'll flip this line up to the charge valve, but they'll leave that loose. Okay? So then this is isolated. So what will happen then is that this valve, the king valve, will be closed. That valve will be closed. But the technician will come back and he'll crack this valve a bit, and this line will be loose to the charge valve, but it purges that line from any air. Okay? So that'll be purged. He tightens that back up. Okay? Once that's purged, there's nothing in it. Then the charge valve is open, the king valve is closed. Okay? Then they start the compressor. All right? Take this up for you here. They start the compressor. Okay? And then they run the compressor and they basically fill the system up. The evaporator's turned on, expansion valve. Okay? And then the whole system is run. This is closed, but everything comes back into the receiver and the receiver fills. Okay? Then when you get to the point where you have the correct amount of weight in it and the receiver liquid level looks good, the system goes up to pressure, begins to operate properly. They cut it all off, shut it down. Okay? This is isolated, that line is drained off, the king valve is open, and your system is ready to go. Alright? So I will write that out for you. Okay? But the main thing is the king valve is isolated, okay, and the charge valve does all the work, and then the system is run, so it's basically dead ended back to the king valve. And then this will be empty, this will fill right up to its liquid level. Everything runs. You put cooling water, you have to run the evaporator and everything like it's normal. Okay, you might want to sometimes put a little bit of a load on it, but the whole idea is the expansion valve works and the whole system works, and you just by the filling, I've seen systems when they're charged is during the charging procedure, everybody's running around, they're looking at the different components of the system to make sure everything's working okay. And the good thing about doing this is you can stop it and start it anytime you want. You can stop the system, you can close that valve, you can check things out, and away you go, right? Okay. So. Okay. Okay, so, beginning. All right. As I described before, we do this, of course, to add refrigerant to a system that's short, or it's normally done with a system that needs to be built. Okay. Step one is that the refrigerant C1 cylinder, okay, which is a storage cylinder, or sometimes they come in drums, or sometimes they're even on a truck. Okay? Okay? But it's placed on the scale. scale. Okay. Okay. And it's usually on its side. Its side with, okay, the bottom elevated. Okay, why? Why is the bottom elevated? It's actually on that drawing there. Okay. So we have our cylinders. They are about, some of them are about this big, some of them are even bigger. They're big giant things, but they basically lots of them. But this is blocked up, okay? Usually there's a big block here, or there's some sort of thing. Anyway, so it holds it up. Why is it like that? What's this here? And what's that there? It's all refrigerant. But what type of refrigerant is this, and what type of refrigerant is that? That's right. The bottom is liquid, the top is gas. Okay? So obviously, if you look at our system here, we've got to add, we're adding it liquid. Okay, there's our expansion valve. So the main valve's closed. We've got nothing in our receiver, so we've got to add liquid refrigerant to our system, and then it goes to the expansion valve, and it expands, it goes into the evaporator, where it's all evaporated off, and then it goes to the rest of our refrigeration system, of course, which the next piece is the condenser. So then it gets condensed in the condenser. Okay, so this is how 99% of the time the systems are charged. The old tech guys, they might add some gas refrigerant to the system, but normally this is the way it's done. And they, even the old tech guys would come to the house and they always dump the receiver upside down so that you're only adding liquid. Okay? If you added gas to this, it wouldn't work right. Okay? Because then you have a bunch of gas on the liquid side and you got to condense it all. Actually, what you have to do is open the expansion valve and get into the evaporator and then condense it all anyway. Okay, so that's why that's elevated, and it's the weight it's taken as well. So you start with, these cylinders weigh, could be 200, 300 kilograms, right? Some of these systems take, some of them take a ton of refrigerant. Okay, so, all right. So then, the charge cylinder. Okay, is then loosely attached, to the charge valve. To the charge valve. All right. So why do we loosely attach it to here? Is because we have to purge this line so that any air and non-condensables that are in the system are gone. And we know this is liquid from here, so then you purge that line out, and then you attach it rigidly, and then away you're ready to go. Okay, it's loosely attached to the charge valve. Okay. Okay. Free the line from the cylinder is purged and then attached. Or sorry, they attach or they just tighten up. Tighten up. Good. and ready to rock. Okay, now the charge valve. Charge valve is now open, and the king valve shut. And in most cases, the guys will shut. Most scenarios, cases, the king valve is shut and verified. Okay. First. All right. Now, when a closed and the compressor running. Okay. I can say charge or fed refrigerant until such time as the system will in addition the correct quantity of refrigerant by weight has been added. So, hooks are up, pressure's running, system's running, liquid level comes up to wherever it needs to be. We've added the correct amount of weight. Okay, systems are checked out. Okay, 6. Alright, it's great. Put it back to the top here. I didn't get it. go ahead. 6. Okay. D. Okay. D. Charge valve. Is shut. Go ahead anywhere, yeah. Charge valve is shut. Okay. The equipment is the equipment lines removed. And then the king valve is open. 7. System ready for operation. Equipment. Those steps. What? Those steps. That's the filling. That's the procedure for filling system. Even the system with refrigerant. Yeah, but not the proper procedure, is it? I wrote it out. Okay. Okay, now.
Information that I have worked.
And one last little point here is that, okay, after the system has been in operation for some time, it may be necessary to add small amounts of refrigerant periodically. Hopefully not, especially with an NH3 system. Okay, but that's the way they're usually. We'll put it on the suction side of the system itself. But that is the description of the king valve as it is seen by TSSA as far as the refrigeration system goes. And do not get the king valve confused or call it a charge valve. It is not. The king valve's purpose is to isolate the receiver from the rest of the system. The charge valve is a separate piece of apparatus that's either connected to the system or usually, even a lot of times the charge valve isn't even there, but on the line here there'll be actually an attachment to add the charge valve. And I've actually seen systems sometimes where they'll have a little dryer here as well. The refrigeration valve will have taken the crap out of the system and started. That's basically it. Right?
So, charging valve is what charging.
Yeah, the charge valve is separate from the king valve. The king valve, okay, sole purpose is to isolate the system liquid receiver. Okay. The charge valve charges the system. Okay. All right. So they kind of go through this a little bit in the book here, but that's the proper procedure for the real world on how to do it. Okay. Yeah. All right. Now the next, actually now if you're going to draw this, use this drawing. And we'll skip that one. That's the last one actually, because the one in the book is kind of, use that one. Okay, because that actually shows the one in the book here. It doesn't show the king valve, it doesn't explain the king valve. It does.
I'm curious about that.
Where what?
You urea finishing off there.
Nope. No, that's it. Okay. This lovely thing here is a scale, by the way. The weight scale. Here's what we're going to go on. Okay. And the cylinder has to be tilted so that the liquid level at the bottom will only add liquid. That's how it's done. So, I'll leave that on for a second for you. The next section, and take a little bit longer, okay, is safety. Okay, this is actually objective 8, which is the last part of chapter objective 8. Okay, and then the last section of chapter 11. Okay. Refrigeration safety. Now, we'll do about 10 minutes here and then take a break.
Why not take a break one after this?
You guys want to take a break now?
Sure.
Okay. Sure. You may get asked, you can't say like that, during the charging or the filling procedure, okay, you have to run the system normally, okay, so you run it with the evaporator under load, okay. So think about that. If you don't, okay, I'll do this for you, and I can make it easier to think about it, okay. So, condenser, evaporator, okay, expansion valve, compressor, okay. And we'll actually have it left. Okay, so for that, okay, condenser, compressor, okay, expansion valve. Okay, so we're adding, remember, we're adding, okay, where are we adding? We're adding it right where? We're adding liquid, right? Right before the expansion valve. Okay? So we're adding it right here, okay? So remember, after coming out of the condenser, our receiver is where? Right here, right? Okay, it's just on my symbol diagram and put on there. That's where our receiver is, right? Good. So, we're adding it there. Okay, so if we don't have the evaporator under load, okay, think about it. If we're filling this system, so say our king valve is isolated, okay, and the system is completely empty, so we're trying to run this system and fill it up with liquid, refrigerant, right? So we're adding liquid to before the expansion valve, it expands, we get gas, basically we get refrigeration gas or low pressure, liquid, okay, into the evaporator. So if we don't have this under load, we got low pressure liquid going in there. What's going to happen is this liquid refrigerant is going to stay liquid, right? Because it's not going to evaporate in the evaporator, right? So we can't. And what don't we want? In the compressor. So do we have to run the evaporator under load? when we're filling? Absolutely. Partial load or somewhat load because we got to condense our liquid refrigerant and make our system work. So the cooling water's got to be on the condenser. The whole thing's got to run. You might run it under a small load at the beginning. This is a controlled environment, right? You won't run it under a bazillion, like a ton of load, but you've got to make the system work. So the answer is yes. You've got to run it under load, or you've got to run cooling, if they ask cooling water, secondary cooling water applied to the yes. Because you've got to make the system work. The only thing that we're doing when we're adding refrigerant to the system, okay, it's running normally, it's just that the system isn't charged, and we're charging it. So the king valve here is closed, okay, so the system is isolated. So basically, our charge cylinders are here, we're filling this whole system right up to here. And when this is full, we got the amount of weight that we want in it, okay, we shut this off, get rid of our filling apparatus, open the king valve, away we go, we're ready to rock. So that's a question they like to ask with different nuances, right? Good. Remember, we're adding liquid. Even though we're expanding, we're just changing the pressure, but it's still going to be liquid here. If we have no load on the evaporator, we're going to be trying to pump liquid into our compressor, which you know what happens. Right? Yep.
That's the same thing on the diagram, right?
Yes.
So
this time, yeah.
Right.
So this, okay, is this, okay, so, right? The only thing, our simple diagram, this simple diagram that I draw all the time, I make it simple, I don't put the receiver in it, because it just confuses people originally when I first started teaching. But now, with your knowledge now, you can put the receiver in there, which is after the condenser, okay? So all this stuff is fitted right here. So just imagine this equipment, imagine the system being massive, and our fill equipment being tiny. So it fits in there, right? So this just goes up.
So, alright. Yep. We have it there. We're the charge valve.
The charge valve, okay, on here. Okay, now there's a reason. Normally, there isn't one. Okay, the only thing that'll be on here is there'll be an attachment for a valve. Okay, so if you go look, when you go to a site or if you're on an NH3 system, when you first trace out the system, go try and find that spot, because it'll be there. And all it'll be is an isolation valve. The valve might not even be there, but there might be just a stub. Okay, and the stub will have a cap on it. And then the cap is a special fitting, and then you attach this. When the refrigeration guy comes in, he's got the rest of it. Okay. But no, the charge valve is not there. The charge valve is something you add after. Okay. And remember, the first part of the procedure is you've got to purge the line from this charging cylinder up until this point. You got to drain all the non-condensables out of that line first, then tighten it up, and then away you go. Okay. That's a great question to ask, because if I ask it, it tells me that you understand knowledge of the system. So, you know, and TSA is on both both sections of my third and on my second. Okay. All right. Now the next section is refrigeration safety. One thing I'm going to tell you about this, okay? A lot of this stuff comes from excerpts from this, which I gave you, which is CSA B32. However, I'm going to go through certain sections of this and bits and pieces that's important, and there are questions that I will ask, and TSA will ask in a bunch of, could be, I might give you a complete question on this that's all true or false. This statement is true or false. Blah, 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 blah. Okay? First of all, tomorrow. Yes. This is the last section, and then we're going to do a little bit on the heat exchangers, but I'll go through that at the end. Don't worry. Okay. You folks as engineers, okay, code regulations and code regs. As an engineer, what is your responsibility? Safety. Okay. Okay, you are responsible anywhere in anywhere in Canada, in the province that you're in, you must, one of the prerequisites of your ticket is you must read these code regulations as they pertain to your province. Okay, it is your responsibility. And I've seen the inspectors come in and ask guys, they don't quiz you or whatever, but they want to know where the CSA B51 or B52 is. But normally you'll know the codes anyway, because the operating engineers that are there and the chief will make sure that you know what they are. Okay? Now there's one little statement here. Okay? There are special regulations in every province dealing with refrigeration plants, and every engineer in charge of such plant should be familiar with these regulations. Okay? As set out in B52. Okay. So, the next, I'm going to go through a whole bunch of points here and bits and pieces and whatnot, but they all come from this, which I've already given you, which is CSA B52. Okay, you all know how to copy this. Okay, which is the mechanical refrigeration code. So you can back up this. All right.
You gave a copy of it?
Yeah.
Yeah. Right.
You have it from my other classes. You have it from, I gave it to you in this class. It's on the thing anyway. You should have copies of this from my other class, and you already have it. I gave you CSA B51, B52, ASME code, you already have it. Unless you got rid of all that stuff from last year. Huh?
I don't remember. I don't remember.
Yeah, you do have CSA. Look, it's on there, and it's. I think I did put it on. It's on there from last semester. You should have like several copies of it.
You want to put that? You want to need that for a test?
No. Just what I'm going to go through today. No, you're not going to. All right. Start at number 1 here. Okay. Okay. Any system, all systems. Okay. Over 103 kPa. What's that? No. Over 103 kPa is what pressure? No, what pressure is 103 kPa? Anything over 103 kPa, which is, right. Yeah, it's anything over a hiccup.
Yeah.
All right. Anything over 103 kPa or 15 psi, which means any system. Okay.
Higher pressure.
Yeah. Okay. With 182 kgs or 91. Right, 91 kgs. This is group 1, and this is group 2. Okay. Group 2, what are these? What's group 1 with 100 kPa? Any system with lower, this is the weight of, what are these? Group 1 and group 2 are what? What is it? They're right, but they're refrigerant. Yeah, right, refrigerant, okay? Anything with refrigerant, okay? Remember, refrig is short for refrigerant. Okay? So any system that's bigger than a hiccup, over 15 pounds with this amount of weight at group 1 and group 2, okay, must be designed with a way to get rid of the refrigerant in a case of emergency. And the other stipulation is there must be a way to do it manually. Must be designed to manually discharge the refrigerant to where? Where? discharge it to? We got to be able to manually open the valve and get rid of it. It's expensive, but where's it going? That's right. Manually, okay, atmosphere. Okay, I'm going to get into the okay. In the event of an emergency, you have to be, all systems must be fitted. You must have a manual valve that you can discharge the system immediately into atmosphere. Now I'm going to show you, okay. So I'm going to draw something here. For now I'm just going to put a block here. Okay. And then I'm going to put a valve here. Top of this and be heater. Okay, and take the root structure. Okay. Now, this. That there. Use my 3D drawing there. A little rusty. It's been a while. Okay. In the middle of this, okay, here's our valve. In the middle of this. Okay. Red box. Okay. Glass. Okay. Enclosure of glass. It's got a glass door on it. Okay. The box must be red. Okay. Another code stipulation. No matter whether it's an NH3 system or 700 system, 3 minutes old. Okay, every system outside the building, an NH3 system, any place, places here that have, if you go down to the arena, okay, outside of the building somewhere there will be a red box that has a glass cover. Basically, inside that glass, okay, is the manual dump valve. Okay. The box must be painted red. It has to have glass. Okay. The box is locked. However, in the case of emergency, what do? You break the glass. The engineer or the fire department guys will open that valve because they will not enter the building until that has been discharged. Now, you heard about that accident that just happened in BC about 2 months ago that killed 3 guys. Okay? It's an NH3 system, the pneumonia system. Okay? Killed the operator, and then 2 guys from the fire department, or 2 local guys from the fire department went in, they didn't follow procedure, and all 3 of them are dead. Okay?
I'm on a supplementary stress.
What's that?
I'm on it.
Ammonia, yeah.
So the food was that bad.
Yeah, well, ammonia, I'm going to get into this in a minute anyway. Ammonia, once it gets to be above 10, I used to know this, it's either 10% or between 10 and 18%. Okay, so 10 and 18, so say this room is about down to here. Okay, if that much of this room is ammonia, you're dead. Okay, what it does, okay, is it sucks. You can't breathe, first of all, it'd be hard to breathe. You can go in here with breathing apparatus, but it also, what it does is it actually can suck the oxygen right through your skin. Right? So you can't breathe, you basically suffocate. And that's what happened to those guys. Now, I don't know I haven't heard anything about the accident investigation, but the first thing I want to know is I want to know where that box was, and I want to know if somebody broke it and discharged the system. And I'll bet you dollars to donuts that procedure wasn't done when those two guys from the fire department went in and they didn't check that. Okay, the guy inside, unfortunately, was probably already dead, but if they'd have checked this and made sure the system was safe, they probably would be alive today. Okay? So that's one stipulation, is that valve, okay, should be on the outside. I had the fire department a couple times come to carry for different, not in the morning or anything like that, but everybody knows where that is. When I was at Briar's Ice Cream, the fire department wouldn't even touch that in Simcoe. It would have to be the engineers or the plant manager that punched that valve and opened it atmosphere. Now I'm going to tell you what. The other thing that has to happen here too, this valve, okay, can be the only. It cannot have another valve on that. So here's our liquid receiver. Okay, that's the only valve between that and the diffuser on the roof. Okay, there can't be another valve in between that. Obviously, why? There's another valve, some knucklehead's going to close it, and then it's not going to discharge. You think the system's going to be safe, right? So it's attached directly to the receiver and the system. Okay, this is the liquid receiver. Okay, and it goes directly to atmosphere. It's the only valve. Outside, it's in a red box covered with glass you can break. And then also, it must be fitted with a diffuser at the top of it. And there are stipulations. I'll get into the diffuser here in a couple minutes. But what's the diffuser for? Actually, what is a diffuser? Maybe don't go with the diffuser.
Diffuser is used to dissipate the ammonia.
Exactly, dissipate the ammonia or dissipate the refrigerant. Yeah, so it helps dissipate it. Okay, there's lots of diffusers we have in all sorts of plants. It's the same as a muffler. Okay, it helps disperse it fast. Okay, and it reduces noise, but it allows uniform distribution, so it's not so violent. Okay, this can't be within 7 meters of a window, and it's got to be. I'll read that in a little bit later, the stipulation where it's going to be, but it cannot be within 7 meters of an opening. Obviously, sometimes refrigerants are heavier than air. It'd be a heck of a bad thing if you open it up and then it fills the whole building back up again, right? Okay. All right, so I'll just read the emergency discharge valve shall be connected directly to the top receiver or other vessel used for storing the refrigerant. No other valve, like I said, between the emergency valve and the vessel. Emergency valve shall be installed in a glass front-end box painted red outside of the building and placed so that it cannot be tampered with by any other person than the person that's being called upon. Okay? Now what that means is that it'll be like the fire department's got to be able to get at it, okay, but it's got to be somewhere where Joe Blow from the street can't walk up. And usually they're at the back of the arenas where there's a gate, okay, but the operators, nobody else knows where it is. But some guy can't walk up that's going to a hockey game with punch it and drain the system, right? And that's all that means. Okay, the manually operated valve shall be installed on a horizontal pipe outside the building. Horizontal, what is that? Okay, on a horizontal pipe outside the building. That's vertical. Okay, horizontal pipe. Okay, so that's vertical. Okay, so it's got to come out like this and be on. Why? Why's it got to be in a piece of horizontal pipe? You need a rainbow? It's just, hey, if it was on a vertical pipe, hey, say the building's 30 stories tall, although these systems won't be like that.
So, anything to do with backflow?
Yeah, it's backflow, back pressure, right? That's all it is that you just want to have the ability, okay, so that this basically the refrigerant comes out, it changes direction, and it goes up from there. But the valve itself, it has to do with basically backflow on the system itself. Okay, so you get only the pressure drop across the valve, which there is no. These are designed to have no pressure drop. Okay? It's just a stipulation, so that this line, okay, that's got a diffuser on the top. Okay. That valve is on a horizontal line. Okay. If it was only on a vertical line, what can happen from the top all the way down to that valve? Could you get an obstruction a lot easier on a line that's vertical? Can you get an obstruction on a line that's vertical?
Yes.
A lot easier than a line that's horizontal. That's why. Because you're going to have pressure. The whole idea is that if it's on a vertical line, it can be all plugged full of crap. But you got to remember, there's a lot of pressure behind this. So if it's on a horizontal line, when you open that valve, chances are it's going to now pull the crap out of it. That's why. Okay? That's why they do it. Okay? That's an argument. Now, there's been argument from in Canada from ever is that you can't have any other valves on this line, obviously. But the other problem is too is that when you have a horizontal line, is that if the line does get like they want to put a drain valve on that, but you can't. On the vertical, you can't. Anywhere in the world where it's warm, you don't have the problem that we do here. So that is that. Next section. Okay. Design and construction. Okay. Okay, there's one point about this. You know the refrigeration systems are made up of all sorts of components. You've got compressors, evaporators, all sorts of equipment built by somebody else. That's all pressure tested. It's all tested, certified, TSSA, TRN numbers before it goes in. However, before you can start this system up, the entire system must be tested as a whole prior to operation the first time. Okay, that's just this one stipulation here. And then that's how you get your insurance certificate, and that's how you start. But it's just one thing that I can bring up is that everything has got to be tested under pressure, and it's got to be tested to at least the lifting pressure of the relief devices on the low high pressure side. Which leads me to the next point. What is the difference between what is a pressure limiting device and what's a pressure relief? R-I-E-L, I before E, except after C, relief device. This is a great question. What's the difference? Why do we need them? Start with the obvious. What's a pressure relief device?
Pressure relief device.
We got them on everything.
Relieve pressure when it goes the hole.
Yeah, but what do we call it? What do we call it?
Safety valve device.
Right, pressure relief device or safety valve. Okay, safety valve. Okay, safety valves have a set pressure. Have a set pressure. Okay, refrigeration systems are no different. They have a set pressure. Okay. Okay, what's a pressure limiting device? Why do we use them? Why do we have to have them on a refrigeration system?
We need a lot of refrigeration. Maintain, predetermine, pressure. So
Not really. It's kind of, there's safety. Okay.
But it does it shuts off the system explodes.
Right. Okay. So at
Below.
90%, okay, all systems, if they reach 90% of the set pressure of the safety valves, okay, the pressure limiting device, okay, must shut the compressor or the generator. You know the generator. That's what you got to know in the bridge. Okay, in refrigeration systems, we must have a pressure limiting device in addition to our pressure relief device or our safety valves. The pressure limiting devices. So if our system for some reason gets to 90% of our safety valve, we want the compressor to shut down, the system to shut down, alarms to go off because we got a flipping problem, right? Okay. Because you don't ever want the safety valves to go off in your system because you got to have them recertified and reset afterwards, and you especially don't want a high pressure side of your refrigeration system going off. That's a big problem. So we have pressure limiting devices. So we get 90% of this, boom, our system shuts down. We know we got a problem. That's the difference between a pressure limiting and a pressure relief device or a safety valve. But we call them pressure relief devices and pressure limiting devices. Or appearances, sorry. What's that fancy word? Which is basically the plural verb of apparatus. Okay. Now, connection. Pressure limiting devices. Okay, I'm just going to go pressure limiting PLDs. Where are they in the system? Where do you think? Where's our, hang on, I'll draw. I'll draw our trusty system. And I'll even put the receiver in now. Okay, where are we going to put a pressure limiting device? We're protecting, remember we got the high side and the low side, right? So, high and low side, whatever you want to call them here, right? Okay, well, our safety valves, we obviously going to protect the high and the low side. Our safety relief devices, but what are we going to shut off? Well, the compressor or the generator. So where are we going to put it? After the compressor. We're going to put it after or before? You're right.
But you want to send the high pressure.
Right.
You want to.
You're going to put it, okay, on the discharge valve, okay, it's connected between the compressor and the stop valve on the discharge side. Okay, so all compressors have a discharge valve. Okay, you got to be able to isolate the compressor, make it getting into the nitty-gritty, right? But it must be there. And usually it could be a sensor or anything else, right? So here's your compressor outlet. There's your isolation valve. It's got to be between the isolation valve and there, right? Yeah. So that it'd be useless if it's on the other side. If somebody can shut that, it's not going to protect the compressor at all. So it's got to be between the outlet of the compressor, the condenser, but it's got to be between that and the isolation valve of the compressor. Okay? And it's not necessarily a safety valve. It's usually a transducer, something like that, that will shut the system down. So I'm going to just kind of draw your attention here to this pressure limiting. This shows an electrical airlock, that's all it is. Okay. There's the discharge valve, there's the pressure limiting device. Okay, notice it's connected to the electrical that's driving the motor. Right? Yeah. Here's our compressor, there's our belt driving the motor. There's our electrical coming into our motor. So there's the discharge. There's a pressure limiting device, electrode, it'll shut the compressor down. So, really, okay, I want to draw your attention to that. Okay. On the suction side, we have a relief device. Okay. I'll shut that off. Where are you? Sorry for that, folks. Forgot to turn that off. Or mute it, whatever it is you're supposed to. There we go. Okay, so I want to draw your attention there. Look at on the suction side of the compressor. Okay, there's the relief device. Okay, which is a pressure, safety valve. Well, look where the discharge is going. It's not going outside. It's going to discharge. Right. Discharge is going. It's going to the discharge of the compressor. This is perfectly legal, by the way. The relief valve. Yeah, the relief valve. Okay, it's relieving the low side pressure. Okay, but it's discharging into the discharge of the compressor. Why? And it's perfectly legal to do that. I don't like it, but it's done. Think of what do we have? We got a high pressure side and we got a low pressure side. So basically what we're doing here, okay, if that relief valve discharges or it opens up, it's going to discharge into the high pressure side. Discharge into the high pressure side, it goes up. What if it's going the other way? Can it discharge? Okay, how can, if we have a safety valve on this side, and this is higher pressure, okay, if this safety valve on the low pressure side opens, how can it discharge into a high pressure side? Because the pressure is lower, it can't. Right? That's right, it's gonna hinder that. Okay? What about the other way? What happens if that relief valve is on the high pressure side, okay, and it discharges into the low pressure side? Save the refrigerator. That point to the high pressure liquid, right? Yeah. No, no, it's not. It hasn't gone to the condenser yet. High pressure vapor.
It goes straight from the
Right. It's done. It's done, but okay. I'll just read what I'll just read what the code says. Okay. Okay. Discharge and pressure relief devices. Okay. Pressure relief devices may also discharge into the low side of the system provided the pressure relief devices are of the type not appreciably affected by back pressure and provided that the low side of the system is equipped with pressure relief devices. Okay. So basically, what does that statement say? If we have a safety valve on the high pressure side, instead of it going down through, we can, in some cases, discharge it to the low pressure side, provided that the low pressure side also has safety relief devices, and it doesn't affect the discharge of the valve itself. It doesn't give you back pressure like any other safety valve, right? I've never been a fan of this. Anyway, if the safety valve's going to lift, I want it to go outside, but they do this in order to save refrigerant, basically. The relief devices on the low side of the system shall have sufficient capacity to protect the pressure vessels that are relieving into the low side of the system, or to protect all pressure vessels on the low side of the system, whichever relieving capacity is the largest. Okay. So here's our glass box. There's our receiver. Okay. This one is going directly where? This is what the way most systems are, most systems I've seen, and the way that any new system is put in. On the receiver, we have a pressure relief system or a dual, okay, and it's going directly where? Right, outside. Yeah.
No, just looking at the box, there's a glass one.
Yep.
It's on the horizontal.
Yeah. That's the way most systems are, right there. I personally wouldn't want to see the high pressure side discharge all of a sudden into the low pressure side of my system.
You are relief valve.
Yeah. Yes, lots of times it's dual relief valve.
So that valve that can close one side.
No.
Yeah.
Why do we have dual relief valves? It's simple. It's money, but
If one side feels.
no, they both have to be at the same set pressure. You can't have two, but you have two valves. Okay? A 6x8 safety valve is $20,000. Two 1.5x2s are $800. Same capacity.
So the two valves replicate the capacity at one valve.
Exactly. Yeah. So the two of them add up. You can have. That's why a lot of you see some boilers. They have. I've seen 3 low pressure safety valves on them because they're cheaper than one big safety valve.
So the two of those different.
Yes, they'll have the same set pressure. They have to by law, and their capacity, the net capacity, is the same to relieve the whole system. So you can put smaller valves in as long as the aggregate or they add up to the capacity that's required. It just saves money that way. Okay. Now, lovely ammonia. Okay. A lot of ammonia systems, okay, instead of, especially the ones like Brad's ice cream in downtown Simcoe, their ammonia release system is fitted with this. Okay, Ammonia, okay, mixes readily with water, or water absorbs it really, really, really well. Okay, that's why it becomes in fire environments, it can become explosive because it mixes with water, and then ammonia under high temperature situations actually burns. So then, literally, in most firefighting applications, you actually suppress the fire by using water to cool it to stop the fire. But the problem with ammonia, if it's mixed with ammonia, it's readily absorbed into the water, and then literally steam becomes explosive that you're trying to cool the system with. That's why it's a really dicey thing. However, what do we do with ammonia systems? Is that the relief valves go into a tank that is protected from freezing, okay? And it has a certain volume. There can be nothing but pure water in that tank, and then it's vented. Okay, and there's two reasons for this. I'll get into the other one in a second here. Okay, the stipulations are 10 liters of fresh water is provided for every kilogram of ammonia. Okay, so 10 liters, ratio is 10 liters for 1 kilogram of NH3. Must be prevented from freezing. You can't add anything to it to stop it from freezing. The tank must be vented, obviously, and have pipe connections that go through it. And this is normally what's done, especially in Cary. We didn't have it because we're on the outskirts of town, but in Simcoe, it's you have that tank there. Now, there's another reason that you may not think of. It's actually pretty funny. Well, let's get into your physics. Okay, so we got an NH3 system. So we got a receiver right there. Okay, and we open a valve. Okay, and we're going to. Doesn't matter, we're going straight to atmosphere. So this is wide open. So we got an NH3 tank in the room here. We open it up, it's going to atmosphere. How fast do you think that tank will drain? Yeah, you would think, hey, why open this? This is a pressurized tank with ammonia in it. Okay? I open that valve, it's gone. It evaporates off and away it goes. Fast. It's not what happens at all. Okay? What happens here is that you've got to boil off all this refrigerant that's in there. Sometimes it could be tons or hundreds and hundreds of pounds. It's got to boil up. Hey, when this is boiling off, what is it doing? Cooling, right? Cooling, it's cold. It'll freeze your hands, freeze you, freeze everything else. So what happens is that eventually the top of this, okay, it reaches saturation temperature or boiling point. Okay? So in order to keep that boiling, we got to keep getting it. It's got to take energy from somewhere. It's got to cool. It's got to boil off. Well, what happens is this surface area gets there. This tank ices up. It immediately freezes like crazy, and then we got no heat transfer. We got to basically force it. So basically, what will happen is this tank can take hours and hours and hours to drain, because once it reaches saturation temperature, boiling point, it stays there, and you've got to keep adding energy to cool it down. Well, the air gets to it, it forms a huge ice barrier, and we get no more saturation temperature, and it sits there and gurgles. Okay, that's another reason that we use water. It goes right into that water tank, it's absorbed, and that tank drains 10 times as fast. You might get a goofy question like that. Why? Just remember that. You'll see that. I mean, the tank will just freeze up. The other thing it can do is it can freeze the lines too. The whole line on the way up can get frozen, and then you get basically the So if you sit there, you can't get any, it doesn't reach saturation temperature of boiling point anymore. Okay, one other point I want to touch on for a second is materials. Okay, and then fusible plugs. Okay, what's a fusible plug? Matter of type. Yeah, it's the same. It's just like a safety relief valve or whatnot. The fusible plug.
That's certain temperature.
Right. Remember, these safety devices, most of the time, the safety valves are there for fire. So the temperature gets up, the fusible plug melts, the system drains, and away it goes, and then vents to atmosphere. Same thing. Same thing with rupture discs with the safety valves, okay? Okay. Fusible plugs are connected as nearly as practical directly to the pressure vessel or other parts of the system being protected above the liquid level of the refrigerant. Okay? But on the fusible plugs may be located above or below the liquid refrigerant level, except on the low side. Okay, why? It's kind of an interesting question, actually. So we can have fusible plugs on both the high and the low, above and below, okay, the liquid level line. But on the low pressure side, it's got to be above the liquid level line. Kind of a trick question.
That's to be on both.
Yeah. It's kind of a trick. Think of some question or some, okay, on the low pressure side, or say subatmospheric sometimes. Some systems, yeah, they operate below, they operate in vacuum conditions, right? Okay, so if you had a fusible plug on a vacuum system, it really wouldn't do too much. Okay, on the low pressure side. On the high pressure side, you can have it on the liquid, above the liquid, below the liquid, doesn't matter. If it heats up, that melts and away it goes. On the low pressure side, it actually can suck it in instead of expending it. Okay. It's just a kind of a silly question, or that I've seen asked before, right? Okay, the other thing that you want to make sure of is that the pressure relief devices are suitable to the refrigerant within the system. Okay, relief devices. Okay, they are suitable to the refrigerant. Okay, so the material. Okay, what happens when we put copper on an NH3 system? Copper and brass on an ammonia system. It's corroded. Yeah, it'll corrode it. So we have a safety valve that has that material. It's got to be suitable with the NH3. That's why safety valves for an NH3 system are so expensive for the material. You can't use cast iron, obviously, but all right. That covers that. Let's take a break for 2 minutes here. All right, and then we'll go into the last few sections here. And then
Enough about material.
all right. All right. Now, the last couple points is health and safety, or TSSA, exit from cool rooms and posting of instructions. Okay. Now, as you know, refrigeration systems are a little bit different. There's compressor rooms they're standalone, just like boiler rooms are standalone. Okay. However, outside of every compressor room or every NH3 room, okay, there's a bunch of equipment that's required. There's going to be basically a Scott air pack that's required. A Scott air pack or mask on air. So So basically, it's required by law, and that's what these sections are about. Okay, you have, it's the duty of the owner. Okay, you say like that. It's the owner. Okay, not TSSA, not the chief engineer, not the operating engineer, not the insurance company. It's the owner's responsibility to provide. Okay. In a system with group 2 or group 3, the owner of the premises to provide and maintain one mask of helmet where amounts of, anyway, one mask or helmet. Okay. Okay. I always use the example of Scott Air Pack. I'm sure you guys have been trained on different ones of that, but that's, you gotta have a breathing apparatus so you can get into the room and not die. Or you can get, it's not for you to get in, it's for you to get somebody else so they don't die, so you don't die with them. Okay? So, the stipulations is that where the amounts of group 2 or group 3 refrigerants between 45 and 450 kilograms. Okay, group 2 and group 3. Okay? Group 2 and group 3. NH3 is group 3. Okay, most of you will be using NH3 because it's sort of toxic. Okay, between 45 and 454 kilograms, which means it's anything that's industrial. Okay? If more than 400 up to, okay, that's 1 up to 454 kg. Okay? That's 1 greater than 454 kgs of refrigerant. Okay? 2 masks. Whether you got twice the chance of dying or you got 2 more cuts in the hole, but anyway, yes. 2 masks and helmets should be provided and maintained. Okay? Most places will put 2 on anyway. Okay, only complete helmets and masks marked as approved by a competent enforcing authority suitable for the refrigerant supply shall be used. They shall be kept inside a suitable cabinet located immediately outside the machinery room or another somewhat accessible location. Hey, they gotta be, you'll go into the compressor rooms and they'll be right outside the door that you enter. You're gonna be able to put them on and get in and get somebody out. Okay? Canisters or cartridges of helmets or masks should be renewed immediately if they've been used or the seal's been broken. Used canisters shall be renewed no later than canisters or whatever. Okay, so basically they gotta be maintained. Okay? Everybody know what I mean, the canisters or cartridges? Yeah. So you have, instead of sometimes, I would say 90% of the places will have air packs, will have Scott air packs. Okay? The cylinder stuff, I mean, to me it's a cheap up, but most places, because of insurance, they use the Scott air packs, canisters, and we'd have canisters and cartridges on the ships because there's some areas that you just couldn't get in with Scott air packs. But all right,
So that's the responsibility of the owner.
Owner, not anybody else. Not TSSA, not insurance, it's the owner. Okay? That's a good question to ask. Hint, hint, hint. Okay, last 2 sections. This one. You ever been stuck in a cold room? It's not fun. I got stuck when I worked in high school. I worked at Mr. Silvery, and I got stuck in the friggin' refrigerator once because they never maintained the door to get me out. It was not a lot of fun, and lucky I screamed loud enough so somebody could hear me from one of the customers came back and got me out. Because the door, you have to have a push handle, or you have to have a means of getting out, right? Oh, it was broken. So anyway, any enclosed space that is maintained the temperatures are harmful to health. Okay? Anything. Can be entered by personnel, shall be equipped with a door that can be readily opened from the inside, and it must have at least one of the, most places now will have the audible alarm. Okay, if you're stuck, you're incapacitated, at least you can phone an alarm. An axe attached by a breakable chain. I don't know what you're going to do with an axe inside of refrigeration. You're way out, I don't know. But anyways, usually the suitable alarm, okay, in case you can't get out, but walk-in freezers and all sorts of stuff. And especially in big, cold storage building. Okay? And the other one is posting of instructions. That is a big one. You can't get your insurance certificate without posting of instructions. Okay. On that card, okay, paying more than in charge, okay, the dear practical refrigeration compressor giving directions for the operation of the system, including, okay, if there's a breakdown and leak, instructions for shutting down the system, name and address of the engineers or the operators, and the other thing is the service guides. Okay? And the inspection department, of course, instructions don't apply to the department. That always happens anyway, automatically. You have something like this. Okay, but the key thing is here, where do they get posted? Is it inside the room or is it outside the room?
Well, couldn't be that would be in a
Right, but whatever, instructions for shutting down the system in case of an emergency. You have emergency shut-offs outside the room. Most plants with conscientious chief engineers will put them in both spots. And most plants with half decent health and safety committees will put them in both spots. There'll be one set. This code says inside the room where the compressors are. Okay? And most places will put them outside as well. But that's usually where they are, is by the compressor bank, or they're on the inside. You're shutting down the system in the case of an emergency. It's not to the point where, it's either something's going wrong, you can shut down the system. Okay? But it also gives you the day and nighttime numbers. But these will, in most cases, as you probably already know, is that there'll be one by code inside. Usually there's another set outside, and there's always a set in the control room. Okay. Regulations summarized under the preceding heads are only some of those contained in CSAB 52. The student, okay, or you should thoroughly be familiar with the entire content of the code. It's your job as an engineer to be familiar with the code itself. Okay. But the posting of instructions, they're the main points that you get questions on, and that I will ask basic questions on any of it. Okay? That thusly ends the part on, that officially ends chapter 11, and the safety part of it. Now, there will be one question on this whole section, and it'll likely be a true or false, and maybe a little bit of multiple choice or whatever with the high points in this. I've actually answered essay questions on this stuff on my second, but this is one topic that is actually, it's better to do short answers than there's a lot of things. Not like a compressor or system, right? So, but it'll be a question that you can obviously you'll have choice. You don't have to do it. You do one of the other ones. So that ends that. Last chapter number 12. Okay. Now, I'm just going to go through objective 1 and objective 2. I made through a question on it. We've done this twice before. This is probably close to the third time. Objective 3, 4, and 5, the other, I'm going to go through that the last lecture class. However, objective 1 and objective 2, shallow tube heat exchangers. Okay, we've done those already before. Okay, and the condensers and the evaporators. Okay, double pipe heat exchangers. Concentric pipe heat exchangers. If you remember this, we did this at the beginning. My first question about these, okay, and I'll just flip over and have a look at this, and the picture at the bottom there. Okay, I want to make one point here. Okay, it's not there. It's kind of a bad drawing here or whatever. But this, look at this picture here. Okay, used to have just a single tube, right? Okay, within a tube. Okay, and then we added, okay, so then we added fins to them. Okay, so they have fins all the way along. Okay, just like a radiator, right? And then what we did is we put the fins, okay, and then these are the fins, and then we put a tube around the outside of it, right? So if you look at this, so there's a tube outside, the fin tube, okay? Why do we do that again? Because we used to just have straight tubes, but then we put fins on them, but why do we do that? Exactly, increases the heat transfer area, increases basically turbulent flow, okay? Remember what the difference between what lamellar flow and turbulent flow is? Okay? Lamellar flow is just like in one line, it's not turbulent. We want, in heat transfer, we want turbulent flow. Why? We don't want the water going through, lazily going on. We want it to pound into the surfaces. We want it to be, basically, we want it to be turbulent. Because why? Same idea. We have turbulent flow. What do we have? What's better? Right. Turbulent flow equals better heat transfer, period. Okay, better heat transfer. Better heat transfer equals what? Right. It's better efficiency. There's one application where you can use the N word or efficiency. You get better efficiency, but basically you get more bang for your buck. You have turbulent flow, okay, and you have tubes that have a bunch of fins on them. It's the same reason why the vectors now we put fins on them. Whereas the old days you just had radiators, they didn't have fins on them, and all you had was the holes in between, and you hope the air got in between them. Well, now we have basically we put fins on them, and then we have little motors so that we get transfer. Okay, we force turbulent flow, so we're a smaller, basically a smaller compact unit. We can get more heat transfer, so it's more efficient, but we get better cost recovery. We get better heat transfer. Everything that's all over the almighty God. Now, having said that, if you look at these, okay, just look at that system, look at one of that, look at that unit, okay, and then just look at a shell and tube heat exchanger, okay. Why do we see a lot of these anymore? There's a lot of them out there, but if you and I were to go into a brand new plant, what type of heat exchanger would we like to see? A shell and tube or one of these? No, it's not plate. This is just a double pipe heat exchanger. What do you think we'll likely see? What do you see more of nowadays?
Couldn't testify to say see more.
Okay.
Most likely to be double pipe.
No. Actually, it'll be shell and tube. Reason being, okay, look at the design of this. Look at all those fins. Look at okay, this is pretty intricate. Adds cost. Okay, these are basically, and if you read through this, but these are for small heat transfer loads. Okay, but they're very, very expensive. to the high pressures and high temperatures. But if you look at those, if you're producing those studs or okay, they're pretty intricate, and with all those, those all going to be welded on. Costs. Okay, longitudinal fin, shield fin. Okay, you got something like this, and if you're into something like a double plate heat exchanger, these are very, very intricate, they're throwaways. You build them once, and if you need more, you just keep adding on more and more. Okay, they're very, very expensive. Whereas the old shell and tube heat exchanger, why is this thing still on? Hang on. Sorry, I apologize. There it goes. All right. Okay. So shell and tube heat exchangers, they're everywhere. They're everywhere. We're going to get into another type actually next week. However, these are relatively speaking, they handle larger loads, they're less expensive, they're easy to manufacture, and they're very easy to, these aren't throwaways. You can take a tube bundle out, order another tube bundle, and away you go. With these, you have a tube within a tube like that. If one of these fails, that's it. These are all welded together, basically. Okay, they're very, very expensive to make. Like look at the intricacy of the, you've got all the flanges, you've got all that stuff that's got to line up and manufacture. These are fitted, basically, into plants. Okay, much more expensive. They don't give you a lot of heat transfer in comparison to a shell and tube heat exchanger. So in most instances, nowadays you're going to see shell and tube versus these. Okay, but you will see them from time to time. Where you probably will see these, if any of you ever worked in an oil petrochemical plant, you see some of these on the high pressure, 1,500 pounds, 2,000 pounds, or 1,000 kgs an hour, something like that. Okay. One thing I want to make a point about though, okay. How does expansion? How do you take care of expansion with one of these? Kind of a trick. Not really a trick question, but it is. But it's part of the inherent design. Okay? Because what's that look like? There you go, expansion. So when that goes like that, okay, you got all these bends. Okay, that allows for the expansion of the unit itself. One of these, there'll be a fixed support. Okay, and then this thing will be allowed to float a little bit. The same thing on, on big piping systems. You'll see the expansion joints. Toyota, you'll see an 18-inch piece of pipe. You walk out of the boiler room and into the plant. All of a sudden, they go 50, 100 feet this way, 100 feet that way, 100 feet back here. Okay, that's the expansion joint of an 18-inch piece of pipe. Okay, so inherently with that design, they allow expansion just by the fact that they're here. Okay, brings me to the next point. How do we allow for expansion in our shell and tube heat exchanger? Okay, we got a fixed tube sheet and a U-tube sheet. Okay, this is the U-tube, so yeah, exactly. So basically, okay, this U-tube, okay, this is held rigidly here, and it's allowed to expand that way. So it expands like this. Okay, this is what we call a two-pass. Really, 1, tube. Single pass heat exchanger. Still the same thing, it's just shell. Okay, single pass, basically you just have a inlet here, and the single pass tube sheet, you basically go in this way and out that way, and then your cooling medium or whatever is going through here. So the tubes go that way. So, however, a fixed tube sheet and a U-tube. Okay. I want you to look at this right here is a beautiful little thread. This is a great thing. You'll see some of these ones, some of the engineering. Oh, I'll do that up. Okay. Don't really worry about that. Okay. You look, split flow, double flow, whatever. Look at this across the top. But look at the far column on the right. What does the far column on the right tell you? Floating head, stationary head, rotating head, whatever. What was I just talking about? Expansion. So this lovely little chart here tells you, that last column tells you how that type of heat exchanger, how expansion is accommodated.
So, like for P, you said, outside parts, rotate.
Right.
Or is that big part?
Yeah. So it's an outside pack floating head. Okay. You notice there, that's packing right there. So this, okay, there's the packing right there. That's bolts. Okay. So this floating head means the head floats and it expands. That's what that means. And it's sealed by that packing right there. Okay. Split flow, two pass longitudinal baffle. Okay, so we got flow in and flow out. One pass shell, in and out. Okay, this just tells you how they are allowed to expand. That's all. Most times, okay, you're going to deal with heat exchangers that are kind of like this. The inlet and outlet will be at this end. Okay, and then this will be rigidly fastened here on this end, and the tubes are allowed to expand on the inside of the shell. That's normally how it's done. Okay, and reboilers, this stuff we're going to do in the next lecture class. Whatever, but that's why this is such a valuable little thing. It tells you exactly how the expansion is accommodated. Okay. That is the main thing with any heat exchanger is that you want it turbulent flow, obviously, so you get the maximum amount of heat transfer you want. You have to want turbulent flow. Okay. And you must have expansion allowances. That's it. Then, the last thing on refrigeration systems, this is especially important. Okay? Is we need loads. Okay, so why do we have baffles?
Baffles are generally used for refrigeration.
Right. So baffles give us turbulent flow, which is equal to better heat transfer. Right? Gotta have baffles, especially in refrigeration systems, because a lot of times, say we're using a condenser or a evaporate, doesn't matter, it's a condenser. Okay? So the top half is what, and the bottom half is what? It's a condenser. So we're condensing what? We're using a condenser in a refrigeration system. We're condensing what in the condenser? The refrigerant, right? Okay, so that means in our condenser we're going to have two phases, right? We're going to have liquid and we're going to have gaseous, right? So in refrigeration systems, the baffles become doubly important because we got to force our heat transfer through that because we're going to have two phases in here. It's not like it's a steam heat exchanger or a water heat exchanger, it's filled all the time. So that's why condenser or shell and tube heat exchangers, okay, for refrigeration systems contain many or a large number of baffles. And that's simply because we're dealing with two phases. We're going to have a gaseous state and a liquid state, so we've got to force that all the way through so we get better heat transfer, we get better efficiency, but it ensures that we get, basically we're condensing, we go in as gas, and we come out as liquid. And that's also another reason why heat exchangers for refrigeration systems are very, very expensive. It's because the design is inherently, there's a little bit more to the design, let's put it that way. Okay. Then there's two types of baffles here. Okay. And what are sectional, and that's what they call donut. Now, I have never, ever seen this. I've probably taken apart or seen hundreds over the years of heat exchangers out with the two bundles out. But I've never seen a disc or a donut baffle in any one of them. So if you ever see one, take a picture and send it to me. I've never seen it. I only ever see these. And usually sometimes it's just baffles that are basically I'll show you the entire tube sheet. It's one big baffle, okay? So here's our tube sheet, there's the head. Okay, and we'll just do this. Okay, so usually you'll just see a baffle there and a baffle there, and they go right from one side to the other. Okay, not like the sectional baffling, and then they're just filled full of holes. Okay. But I've never seen a disc or a donut baffle yet, but it's not completely done yet. So and lands there, body there, bolts, and there we go. Again, a little bit of reading on that, but again, this is just rehashing what we've already done. Okay. So that is basically the end of that. Now, again, what I'll tell you here is where the questions are coming from. No. And this is on, I put it all on weekly learning, it's all in there, but I'll just write it down here. Okay. Chapter 11. Okay, objective 1 and 2. 2 questions. Objective 3, 4, and 5. 2 questions. Objective 6. Okay. Which is refrigerant addition. Okay? 1 question. Okay, that is your question. Okay, objective 8, which is the safety. 1 question.
That one is the second line. 3, 4, 5. Watch up there. In chapter.
Same chapter. Yeah. 3, 4, and 5. Objective 8, which is safety. 1 question. Okay, and then 1 question from the previous. Okay, and then there'll be 1, I could put 1 question on shell and 2, which is actually previous anyway. Okay. So you only have to do 5 questions, you're going to have 8 anyway. 8 questions you can choose from, you only have to do 5. 2, 4, 5, 6, 7, 8.
Some of the time. You want to plan to do that.
No, the time you're going to get, you get 100, you'll get 100 minutes, which is plenty of time. And then next week we get to do the rest of it, which is reboilers, plate frame heat exchangers, and then you've already done cooling towers. There's a few sections on the cooling tower you want to touch on, and then I'll do a review. All right. Any questions?
Can we get action first?
You can get what?
That's a question. Can we get action first?
You get them tomorrow. How's that?
I'm going to do about patient. Today we better. How about that?
Tomorrow. There might be 1 question that most of them, not multiple choice, but 2 of them.
That's first and fourth.
Yeah.
Fourth is in the book, right?
Yeah, but don't read the codes in the book. Just do what I gave you. That's all I'm going to ask. What's in there and what I gave you. That's all. Don't read the codes, they'll just confuse the issue because they're too worried. Just what I gave you is what's going to be tested. And what's in the chapter as well, which is the same thing, that only I deciphered what they put in here and gave you, put it in layman's terms rather than the gobbledygook that they wrote. Yeah. I just gave you I changed that into real words anyway. But that's where everything comes from. You can read the code book if you want, but it's just, all you need to know is what I gave you and what's in
No, not really the code book, just in the manual, code part.
No.
Well, read it from the third class.
Yes. No, this is chapter 8. Yeah. That's just it. Exactly. Which is exactly what I went over. I just gave you the proper, an easier way to interpret it, that's all.
chapter 8?
Objective 8. Objective 8 in chapter. Okay, these are all, there's only 3 chapters in this whole course.
Subject is in chapter 11.
Yeah, chapter 11, chapter 12, and then the first chapter we did is, yeah, it's 10, 11, and 10, 11, and 12.